Well, good afternoon. Welcome to Chemistry B, Unit 5, Equations and Stoichiometry, Day 2. Let's get started. Today we're going to talk about the types of equations. On our first video, we talked about what a chemical reaction was. We talked about the three types of changes, physical, chemical, and nuclear, and what they entailed. They talked about the parts of the equation, the products, the arrow, which means yields, and reactants. So today we're going to talk about types of. The first type of equation is called combination. It's also called synthesis. Let's watch this video.
Alright, there are millions and millions of different types of chemical reactions that take place in nature. One of them that you might see in class would be the synthesis reaction, also known as a combination reaction. This is when a chemical or two or more substances react to form a single product. That's your clue that it is a synthesis reaction or a combination reaction. It's a single product. Okay? It's when one substance combines with another substance to form, again, a single product. That's your hint. Okay. So what kinds of things will undergo this? Well, we have two elements that can come together. We have the sodium metal that can combine with chlorine gas to form our table salt, sodium chloride. Notice we have, just because there are two of them, doesn't mean that this is not a single product. If you have just one product over here, no plus signs, that means it's a synthesis reaction. Another type is when carbon reacts with oxygen gas to form carbon dioxide or carbon monoxide. Now notice that this one, there's only one possible product that can take place, because it's ionic. We know that ionic compounds can only have one type of compound together, or one possible combination. However, these two are non-metals, or are gases. We can have several different types of products. We can have either carbon dioxide or carbon monoxide, depending on what actually is happening here, or possibly both in separate different reactions. Or two compounds can come together. We have calcium oxide combined with water to produce calcium hydroxide. Notice again a single product. Or a compound and an element can come together. Sulfur dioxide plus oxygen gas yields two sulfur trioxide gas particles. I do also want to note that because these two react with oxygen, these also can be classified as combustion reactions, which you can learn about in another video in more detail. Alright, so let's actually look at a video describing what a synthesis reaction looks like. So we have combined sulfur particles and iron particles. Sulfur is the yellow and iron is the black. And we're going to combine them and mix them together to form a mixture. And so we can have all mixed throughout in this beaker. And then what we're going to do is we are going to put it on the table. And so we're going to spread it out so we have more surface area. So because the greater the surface area you have, the better reaction is going to take place. So we're going to pour it all out on the table. And then we're actually going to require a little bit of energy. Okay, so an energy in this case is going to be in the form of heat. So we're going to bring over a Bunsen burner, which you probably have seen in class. And we're going to light it, and we're going to actually use a glass rod. This is a Bunsen burner. And we're going to actually heat up the glass rod so we can actually have some energy, some thermal energy in this glass rod. Okay, and this actually, for some reason, takes a really long time in this video. So he's going to heat it up because glass does take quite a while to heat up and actually retain that heat. And then we're going to touch it to the mixture that we have of sulfur and iron. And notice this huge amount of energy that was released. Okay, that is showing us that all synthesis reactions are exothermic, meaning it releases energy. It might require a bit of energy, but it releases a lot more than it requires. And now we have a new substance. This is iron sulfide. Okay, that's our new substance. It has different properties. It completely reacts differently. Notice it's all big block of a new compound. That's an example of a synthesis reaction, one of the reactions that you'll see in class.
So as you can tell, that combination reaction or synthesis reaction, as Super Science Babe called it, is where two or more substances react to form a single new substance. We're going to use our example of magnesium and oxygen. You will see here that we have two magnesium atoms and they are combining with an O2 molecule, a solid combining with a gas to form a solid magnesium oxide. The little S means solid, and that tells you the form of the phase of matter of the element involved in the reaction, and the G obviously stands for gas, and if you ever see a L, it stands for liquid. You will also see something called AQ, which is aqueous, which means the element has been dissolved into solution. Most of the time that means water. Okay? Here's decomposition. Type number 2. Again, super science, babe.
So one of the types of reactions that you'll see in class are decomposition reactions. And decomposition reactions are exactly the way they sound. It's going from a single reactant going to several products. Like when you think of something decomposing, like trash or your biodegradables or whatever it may be, you think of something, your one piece of trash breaking down into its elements, several different products, which is exactly what's happening. You have one reactant, that's your key. This is going to be your clue that it's a decomposition reaction, breaking down into several products. So here's your skeletal reaction. Notice it's one reactant, key to your several products. Okay, so what we're doing is we're going to be breaking the bonds. Breaking bonds requires a lot of energy. So sometimes that you'll need to make this go faster is you'll need something called a catalyst. And a catalyst is something that speeds up a reaction. It actually lowers the activation energy, so you doesn't require as much energy for this reaction to occur. And it actually speeds up the reaction process. So catalysts are typically used in decomposition reactions. So here are some examples of what you might see in class. So you have your single reactants breaking down. You can break down to an elemental form from sodium nitride to sodium and nitrogen. You can break down into two compounds, dinitrogen oxide and water. Or you can even break down into elements in water. It really depends on what your reaction is. All right, so let's actually talk about this one in a little bit more depth. This is hydrogen peroxide. You probably have it in your medicine cabinet at home. And what happens is if you keep it too long, this reaction actually will take place, and it'll break down into water and oxygen gas. So you don't want to keep hydrogen peroxide too long, or else it's going to lose its effectiveness, essentially, and you're not going to be able to use it anymore. So you want to make sure that you actually replace this quite often, because this reaction does take place. Now, it does take a while to do this, but it will do this. So sometimes to make the reaction speed up, we talked about using a catalyst. So let's actually do this, breaking down into water and oxygen gas. Let's actually do that with a catalyst and see what happens. Okay, so right here we're going to call this elephant toothpaste, and you'll see why. So we're going to have a very strong, highly concentrated hydrogen peroxide come into our graduated cylinder. We're going to add some dish soap just for effect, just for fun, and some food coloring just to make it more fun. Okay, and then we're going to add our catalyst, potassium iodide. It's going to speed up the reaction. And notice it's starting to, goes right away, and the soap is actually getting the bubbles from the oxygen gas, and then you're left over with water at the bottom. And so this is an example of a decomposition reaction, just for effect. The soap is in there to make it more fun. Here's another good. There's another good one. All right. So so decomposition reactions are one of the 5 that you'll see in class.
All right. So decomposition reaction is where the compound will break down into 2 or more simpler products. They involve only one reactant and 2 or more products. For example, mercury and oxygen. Mercury oxide, over time, will decompose into mercury in the liquid state and oxygen in the gas state. Okay? A single replacement reaction. Single replacement.
Alright, so we're going to talk about single replacement reactions. You might also know them as single displacement reactions. They're exactly the same thing, just different ways of saying them. It's just when an element replaces another element in a compound. And know that metals replace metals. Non-metals replace non-metals. Non-metals will never replace metals, or vice versa. They only replace itself, or the only type of reaction that it is, or element that it is. So let's look at this simple reaction. We have A plus BX yields AX plus B. Okay. Let's analyze this. So we have A plus BX. We know that B is the metal. How do we know B is the metal? Because in ionic compounds, metals always come before non-metals. Okay? And know that A must be a metal also, because in this case, A is replacing B. Metals replace metals. Okay? So an easy way to remember something like that is to actually think about them dancing. Okay? So we have B, X are dancing together. B is the metal. We're going to say the boys. Boys and girls dance. Boys are typically the leaders. So B is going to lead, and X is going to follow. The non-metals, the girls, are going to follow, and A will replace B in this case. All right, so let's look at something that's actually a real reaction. We have copper, which we know is a metal, and we have silver nitrate. Notice that silver is first, it's a metal. So in this case, silver is going to replace copper. The metals are going to replace each other. So then our products are going to be silver plus copper 2 nitrate. Okay? So how do we know that copper is going to replace silver in a reaction? Well, because sometimes metals will replace metals, but sometimes nothing will happen. So how do we know? Well, we have to go over to our activity series. Okay, you might have gotten this sheet in class. There's no need to memorize it. You'll always pretty much have it in front of you if you need it. We have the most active metals, the metals that are extremely reactive, up at top, and the least active metals at the bottom. Okay? Let's go back to our dancing analogy and say that that magnesium and chloride are dancing together. Remember, magnesium is the metal, and the boy, chloride is the non-metal or the girl. Okay, then up comes along potassium. Potassium's like, hey, chlorine, would you like to dance? And chlorine's like, heck yeah, I would love to dance with you. So ditch magnesium and now dance with potassium. Potassium's a more active metal. Let's go back and say, okay, let's go back to the beginning and say magnesium's dancing with chlorine, and iron comes up. Is chlorine going to dance with iron and ditch magnesium? No. Iron's not as desirable, or it's not as active. Okay, so that's not going to happen. So if it's lower down on the activity series, the reaction is not going to take place. If it's higher up on the activity series, that reaction will take place. And this is the way that non-metals replace each other. Same idea. So let's go and let's do some examples. Okay, so we have potassium by itself, and we have zinc chloride. Okay, potassium is going to go up and say, all right, chloride, would you like to dance with me? You're going to look at your activity series. Zinc is pretty low. Potassium's a little bit higher up. Chlorine's going to be like, heck yeah, I'll dance with you. So what's going to happen is potassium and chloride are going to come together. Okay, so don't mind the two. They have to come together properly. So we have the potassium, which is going to make a plus charge. We have the chlorine, which is going to make a minus charge. Do what we do, and this is a 1 here. It's going to exchange the numbers at the bottom, and you're going to make potassium chloride, KCl. Don't mind the two. We'll take care of that when we balance the equation. And then zinc is going to be all alone. Zinc. Okay, so now we have the balance, and now that we have the products, we have 2 chlorine on this side. We're going to put a big 2 here, which means we have 2 potassiums. And I'll put a 2 here. Now we have a balanced equation, and this is a single replacement reaction. Let's look at the next one. We have iron, who wants to replace sodium and dance with phosphate. So can iron do that? Let's look at our activity series. Iron is down here. Sodium is up here. There's no way phosphate's going to ditch sodium to dance with iron. No way. So that reaction's not going to happen. Okay? I'm going to say no reaction. They'll just hang out together. Then this iron will not be able to react with sodium phosphate. No reaction. Now, this activity series, if you want to understand where it comes from, I would go to the electrochemistry film and talk about it. We talk about the details of that there. Okay, so let's actually see a single replacement reaction in action.
All right, so a single replacement is a reaction where, as you saw, one element replaces a second element in a compound. Both the reactants and the products have an element and a compound. So in this example, K replaces the hydrogen, kicks it out, and replaces it. So now we have KOH and the H2 by itself. How do we know whether a metal will displace another metal? Based on that activity series of metals, lists metals in the order of decreasing reactivity. And go ahead and copy that. You will want to copy that exactly as you see it. And we will pick up in another video with the rest. So part 2 of day 2.